record this portion for just the recap and review. So as I told you, I'm going to go over these two questions, number 7 and 8. So the procedure that we're referring to here in the starch demonstration, so this is the starch and sugar carbohydrate active questions from the lab. This demonstration required just some 2-row grain, so basically grain. And the idea is, well, to taste the grain, if I just put temperature, like room temperature water in it, if you taste the liquid portion of that grain when it soaks up, it really is just very bland. So if I'm referring to those images that you have in the back, you're looking at this molecule right here. Let me get it back into focus. Okay, so you're looking at this starch, a grain, and I use 2-row barley for my demonstration. And the 2-row barley is a very bland taste. And what I asked to do is I said, okay, well, we're going to put a temperature range of 148 to 160. We don't want to actually denature or the actual molecule. However, I want it to undergo hydrolysis. Okay, so I don't want to denature, but I want to undergo hydrolysis. And in order to do so, I need that temperature. So I need a cup with the 2-row barley grain. I'm going to pour that water between 150 degrees, let's say Fahrenheit, and I'm going to let it sit for about 20 to 30 minutes. The longer I let it sit, the more hydrolysis occurs. So I had this bland tasting type of liquid mush because I just put it in the water immediately. But after 20 to 30 minutes, it starts to undergo hydrolysis, which means that it's going to start breaking down into disaccharide and then eventually possibly a monosaccharide. So if we went from having a starch that's a bland taste, the question number 8 asks, well, what is it going to taste like? Well, now you're breaking it down. Well, sucrose is table sugar, glucose, sucrose. So you're looking at, it's going to start tasting sweeter. Because if you're undergoing hydrolysis, you're putting water back in to break those molecules apart, and now you're going to taste sweeter as a result. Okay, so that's answering 7 and 8. I do want to recap these images again, though, so we can clarify it. So we have a monosaccharide. This is not a name. Monosaccharide is a category of a simple sugar, a one molecule sugar. Disaccharide is a category, not a name. It means 2. If we have more than 2, we have something called a polysaccharide. More than 2 sugar. Another way of writing the brackets, if it keeps going, is this little zigzags. That's what those denote. Just means that it keeps going. The starch molecule keeps going. So the way we've brought these two together is by dehydration synthesis. An OH from one and a hydrogen from another, remove, and then we're left with here disaccharide. We have one oxygen left, and that's what links those two monosaccharides together. And that process keeps going until then we have this polysaccharide. So I've given you names of examples. So one saccharide would be called glucose. That's the name. 2 would be called sucrose. That's the name. And then we have starch. This is a specific one, but just the name starch indicates you have a polysaccharide. So I do want to clarify categories versus names of molecules. All right. So it does talk about, and this is the referring to the starch, carbohydrate, and sugar. When I refer back to our pineapple enzyme activity lab, what I do want to go over is on the back, we had a question here and I want to go over it, is number 7. Okay, so I'm just taking my answer here right now to show you. So it asks you, when you make Jell-O, first you dissolve the powder in hot water and then you add cold. Explain these directions using the idea of the kinetic molecular theory. So now we're tying in physics from last year. The KMT, kinetic molecular theory, is, if in my definition, I just wrote down the theory of moving molecules, or particles in this case. So the particles move faster, and then when you add cold water, they move slower. We're going to be using the KMT, the kinetic molecular theory, in upcoming units. So and specifically, that's why I wrote that here. So I wanted to introduce it where it's still appropriate, because that's exactly what the directions on a Jell-O package states. It says, take your Jell-O, the sugar, with boiling water and dissolve it. So those particles are moving faster, and then it's able to dissolve. And then you want to slow those particles down and you add water. So again, I noted what unit is going to be using the KMT, which kinetic molecular theory. It's in the gas laws. And this is why I've introduced it today, or yesterday rather, in your lab questions. Okay, so it's not the main focus, but I wanted a precursor of what's upcoming. And the last thing I wanted to review is a actual molecule that you've seen, and I want to make sure I clarify. So I'm going to draw it out right here. And I'm recording this so that way you have this at any time, these little extra notes, and then I'll go over any questions that you have over anything that we've covered in the past days. All right, so you have seen this image. You have a double bond, double bond, double bond here. Okay. Another way to draw this is if I drew all the carbon instead of just the points, I'd have a double bond, double bond, double bond. And then I have, there's 4 bonds around carbon, excuse me. That means it would have 1 hydrogen. And the long way of drawing this molecule would look like this. Okay, so these are 6. Let me get me out of the, into focus again. There we go. So it's a cyclo, so it's called cyclo. There's 6, so it's hex. There's double bonds around every other. You don't need to indicate where, because a cyclohexene indicates that they're all double bonded. It can't have a double bond on every carbon to carbon, because if that were the case, it wouldn't be a hydrocarbon, because remember, you can only have 4 bonds. So if you had a double bond here, you wouldn't be able to have this hydrogen there. Okay, so the shorthand way, still cyclohexane. And then there's even a shorter way, and you have seen it in my addition polymerization problems. I've even drawn the shorthand way, which looks like this, and you have a circle. That circle just denotes that there's double bonds on every other. So again, I didn't show any hydrogens, that's understood, didn't show the carbons, didn't even show the double bonds. So these are all the same molecule, cyclohexane. Cyclohexane. There is a nickname, I guess, a name that we use in lieu of cyclohexane. Chemists use the word benzene. So this is a benzene ring. Okay, so these all, it's like an arrow, sorry. So these are all can be interchangeably called benzene. So if you were to see this molecule, you could either call it cyclohexane, completely appropriate, but you may refer to this as benzene as well. So benzene can be seen in various ways. Let me just bring this down a little bit here. You could have it in a branch. So let's say I have a branch, and I'm going to use 3 carbon in my branch, and I'm going to draw my cyclohexene or my benzene like this, and I'm going to draw it super shorthand way, just with the circle. Again, they're all the same. In this case, this branch, we're going to use this branch name as benzyl. Okay, so I have 3 here, and this on the second carbon. So I would say 2 benzyl, not benzoyl. That's a different molecule. This is benzyl, and this is prop because it's 3, and there's single bond like this. There is yet another way you could say this. Benzyl is also sometimes referred to as phenyl. I want to clarify something, so I'll just put or. So this is this or this. I want to clarify something though. There is a slight difference between benzyl and phenyl. However, that's something you'll learn in organic chemistry if you ever decide to take it in college. At our level, I just want to give you the options that are possible there. Okay, so the options that are possible. Okay, so we have the 2 branches that are possible. There's different names to it. Again, there's slight difference, but we don't need to know the difference between them. And yet there's another way we could add this. Let's say this is part of an acid. We learned about acids, carboxylic acid. So let's see if we have an acid. And I'm going to, oh, this is a long line, sorry, like that. I'm going to draw it like this time without the circle. Just, that's what I felt like doing. And we have our acid portion, the carboxylic acid portion, which is the carbonyl and the hydroxide attached. And this name would be benzoic acid. The ending is the same, but here we have a benzene ring. So we have benzoic acid, and this is a common name for it. They don't typically say phenolic acid. There's not, it's again, because of the slight differences that I haven't covered with you and then I don't plan to because of the details. But I just wanted to show you these different variations. I purposely put some in the review so that way you can practice it. But also I did this because some of the videos in the Khan Academies, they may refer to this as a benzene ring, and I don't want you to be confused that it's something different other than a cyclohexane. Okay, so I'm going to stop my recording or pause it right now and answer any questions over anything that we've covered so far.